first webinar, as I told you, is about the general overview of EN 1998 Part 4. Given that Professor Butenweg that I will introduce now will have also the next webinar, I suggest to have a unique question and answer session just after the two presentations. Professor Christoph Butenweg is a professor of technical mechanics and structural engineering at Aachen University of Applied Science. He is a visiting professor at the University of Belgrade, visiting lecturer and University and business manager and associate of the engineering company SD Engineering. He's a member of the executive board of the Center for Wind and Earthquake Engineering at Aachen University, which combines and guides the interdisciplinary teaching and research activity of Aachen University in the field of wind and earthquake engineering. He's a leader of PT5 for the evolution of Eurocode 8, Part 4 and 6, and member of the executive board of European Association of Earthquake Engineering. He's a member of the Code Committee NA 516. He's a chairman of the committee task group NA 05637AA, chairman of the International Conference, SEDIF, Seismic Design of Industrial Facilities, and a member of the Research Advisory Board of the German Committee for Metal and Construction. So I will leave the word to Professor Butenweg for these two seminars, and after that we will have the question and answer session.
Okay, so thank you for the introduction, Rita and Fabrizio. It is a pleasure to welcome you to the webinar 4, to the first part of the webinar, which is a general overview of EN 1998 Part 4. So I will start with this general overview, and then I will continue with the second part about silos and pressure function on tanks, and afterwards we will have time for questions. So this Part 4 was developed by the project team 5 during the last years after intensive discussions and development of design rules for these specific structures. And what I have to mention at the very beginning is it is important to know that the new Part 4 is a merged version of the former Part 4 and Part 6, which was distributed to silos and tanks and pipelines in Part 4, and Part 6 covers the towers, masts, and chimneys. So the merging was done because of, I think 3 main reasons. The first reason was that during the evolution of Part 6, we recognized that we were able to condense Part 6 to a couple of pages, because several topics were already covered in the new version of Part 1.2, which is much more detailed than in the first generation. The second reason is that there were several similarities in the design rules of these specific structures, so it was a good chance, let's say, to reduce the volume of the code, which was also in line with our mandate. And the third reason for me is, let's say, a practical reason. So I think as a practitioner, it is really good to have only one document with specific structures that complements Part 1.2 with the usual buildings. So then you can find all the specific structures that are covered in Eurocode 8. And this was more or less the main reason. And what we are going to present today is this merged version of Part 4. And you will not find any more Part 6 because that was running out. So the scope of Part 4 is the design of specific structures. So which kind of structures are covered? First of all, we are covering in Part 4 elevated and on-ground silos and tanks. So this means that we are also covering different geometries: cylindrical, vertical tanks, cylindrical, horizontal tanks, Then we have also rectangular tanks, and we also have some rules for embedded tanks, which are also needed in practice. The second point, or the second aspect, are pipeline systems. So pipeline system means that it's not only related to the pipeline itself, it's also related to installations along the pipeline and interconnections with other pipelines, because this is also quite important. Furthermore, we have here to mention that we need above ground and buried pipelines. So above ground pipelines, for example, are resting on foundations and, for example, pipe bridges. And buried pipelines are usually used for the gas transportation network or the water supply. So then, as I already mentioned, we are covering part 6, towers, masts, and chimneys. And there is a new topic included in part 4. And this topic are ancillary elements attached to the structures that I mentioned before, but also to other primary systems in industrial facilities. So the question is, why is it needed? Because ancillary elements are also covered in part 1, 2. So there are some specific aspects that are specific for industrial facilities, and these aspects are covered in part 4. But part 4 is not contradictory to part 1, 2, so it complements the part 1, 2. And one main reason is that we have to take into account interaction effects, not only with the first eigenmode, also with higher eigenmodes, and some rules for handling this problem are provided in part 4 and will be presented later on. So if we have a closer look on the content, so we have 3 more or less general chapters, and within these general chapters, the variables are defined, the scope, and some basic rules. So what I'm going to present is the basic of design in chapter 4, and then from chapter 5 to 10, we will find the rules for the specific structures that I mentioned before. So 5 to 10 will be presented today, and in the introduction, I'm more or less talking about the basis of design. And this is also quite important to know and to understand the structure. So everything what is related to all specific structures is placed in the basis of design. Everything what is specific is moved to chapter 5 to 10. So that is the basic structure in order to avoid repetitions. Furthermore, it was necessary to include 5 annexes. So the first annex is a table for the seismic design of tanks, which is normative. The reason is that we would like to provide a force-based design for tanks, which can be easily applied in practice. I will present this Annex A, which is one of the main, let's say, changes to the older code or to the first generation within this introduction. So then Annex B is the soil structure interaction effects of tanks. So it complements part 5, but it makes also reference to part 5, so it's not doubled. Annex C is, let's say, these are constructive rules and general design consideration that has nothing to do with the design. But if you are following such rules, you can save time in your design. So these are more or less general rules that you can follow so that you're not entering any problems in the seismic design. Furthermore, we need some soil structure interaction descriptions to the surrounding soil for pipelines. So these rules will be introduced later on. So mainly some spring laws that allow us to consider the effect of the surrounding soil in a simplified way. And Annex E, so I think this is a really special and useful annex. So it was developed by Dimitrios Wambatsikos and his group. So these are design differential surface displacements at pipeline fault crossings. So I think this annex is really helpful to get an idea about the expected displacements that are to be applied within the design of fault crossings. And this is also an informative annex because it is also possible and allowed to use other approaches. So if we look closer on the performance requirements to the structures that are covered by part 4, we can see that we have to meet the performance requirements with respect to limit states and consequence classes. Limit states and consequence classes are already defined in part 1.2, but refined for part 1.4, for part 4, because we have to consider the specific demands of these higher risk structures. So the requirements are as follows. So the first requirement is the protection of human lives and personal injuries. So that is more or less in line with the one that we already know for usual buildings. Then we have to take care for the protection of environment. So that means we should be aware that we are probably handling toxic substance that can be spread into the air, into the water, or into the soil. So we have to be very careful because that can influence the inhabitants in the surrounding or in the region. Furthermore, we need to consider that lifeline systems should be functioning after an earthquake in order to be ready with civil protection measures. And we should also try to avoid cascading effects within plants, so among production units, within one production units, but also we have to keep in mind that some of the plants are placed in regions with residential areas around for historical reasons, for example, and we have also to avoid that there are, let's say, effects on these neighboring regions, which will also cause human lives and injuries. Another point is the limitation of damage to guarantee the functionality. And this will also minimize the economic consequences. So if I have a really long downtime time of 1 year, I will lose a lot of money. So that is an economic reason, but there is also a risk that I will disturb the supply of goods to the people. And this is another point why we have to follow the design rules which are given in part 4. So the limit states that we defined for the specific structures are shown here. First of all, the main focus is the verification of the SD limit state. The SD limit state is defined as we are allowing damage, significant damage, but the structural integrity should remain, and we allow only a controlled leakage of contents, which can be achieved by specific measures. On top of that, it is possible to define also damage limitation and operational limit state. In case of damage limitation, the basic idea is to limit the damage and to have the chance to be faster operational after an earthquake, so I can carry out checking and control, and then I'll be ready, let's say, with the operation of the system again. And again, we have to take care for liquid filled systems that they should remain leak-proof. Operational limit state is more or less one level higher. So this is more or less defined by, for example, the production operator or the owner. So if you would like to continue with the construction, then we have to make it more safe. So what is not covered is NC limit state, although values are given for return periods and performance factors in part 4, but it is only given for the compatibility with part 3 for existing structures. So if we have a closer look on the consequence classes, CC3 and CC4, we can see that CC3 and CC4 are specifically defined in part 4. The first consequence classes can be taken from EN 1990, and CC3B are structures that are important for the public safety and environment. And we should also keep in mind that we should not affect, let's say, nearby buildings or adjacent facilities. There is another criteria for CC3B mentioned in part 4. It should not, let's say, influence the operational of civil protection services. So we should be ready, let's say, to start with these services after an earthquake, and that should not be, let's say, hindered by the damage due to the industrial facilities. The consequence class CC4 is not covered in Eurocode 8, and it is the same as in the other parts, so we are not covering it, but it is mentioned that the principles of design can also be applied in CC4, so that means other codes can make reference to part 4 if they would like to use the principles of design. On the next slide, the national determined parameters for return periods and performance factors are shown. So you can easily see that they are given for NC, SD, and damage limitation. Operational limitation has to be defined for each, let's say, case separately. And please consider that the numbers are higher in comparison to part 1, 2. But these are only recommendations and can be overwritten by the national authorities. Furthermore, there is also the definition of the seismic action class coefficient. The seismic action class coefficient is also increased in comparison to part 1, 2. And just to remind, this coefficient is required for the definition of the seismic action classes: very low, low, moderate, and high. So what are the structural modeling and analysis options? So we have 3 options: force-based approach, nonlinear static analysis, and response history analysis. But the main focus is on force-based analysis, because we would like to have reliable rules and easy to applicable in order to provide load-bearing reserves to these structures. The modeling rules and all other details will be presented later on, because they are included in chapters 5 to 10. So there's one specialty, because we have also several times to handle axisymmetric structures in plan, so like tanks or silos. And for these axisymmetric structures, we are using a different combination rule in comparison to part 1.1. So this rule was developed during the evolution of part 4. It was published, and all the details are provided in the background document. So I will not go into the details, but it was published in a reviewed paper, and it's also given in the background document. So that's what we are using here for the combination. So just a short overview again. So silos and tanks, above ground pipelines, and buried pipelines, and towers, masts, and chimneys. So the main focus is force-based design, and the other let's say, possibilities for calculations are also provided, but let's say in a second line, if we have specific problems, then we can use also these, let's say, more advanced techniques. So they are not forbidden, but it is recommended to use the force-based design to have, let's say, robust design rules. The verification to limit states, so it is mandatory to verify SD limit states, and if appropriate, you can use also DL and OP limit states. As already mentioned, verification for NC is not required. There is one exception: if we can show that the total base shear in the seismic design situation is less than for example, the wind load in the design situation for the regular for the usual load combination, then it is not necessary to verify the SD limit state. But in this case, we have to apply a Q factor of 1.0 and the safety factors that are usually used in the load combinations for wind. So this is an exception. In that case, we don't need to verify the SD limit state and also the other limit states that I mentioned before. So to summarize, what are the major changes? So we have now one part, we merged part 4 and part 6 standard procedures for spaced approach. There are simplifications of tank calculation procedures with pressure functions. And I think one main aspect is also the consistency with the reinforced concrete code and the steel code, which will be presented later on. And we have also new rules or additional rules for horizontal cylindrical tanks and also for pipelines, which were not included so far. And I would like also to mention that we have in total 5 background documents that can be used for studying the details and the reasons for the implementation. So these background documents are available and can be used for a more detailed study of this code. So this was more or less a short introduction into the part 4.